All right. So for this one, it says this is question number 1 from our most recent assignment. Where's my little thingy? So it says, this is question number 1. It says the force diagram above shows a box accelerating to the right on a horizontal surface of non-negligible friction. So they're saying there's friction. We used to say frictionless, but that always confuses people because there's always friction. But basically, they're saying we're gonna have to consider the friction. That's a weird one too, because usually we say there's no friction, but now they're saying we have to count the friction. So remember, friction is always represented by a lowercase f. And then it says there's a tension. So they're pulling on it with some sort of cord that's exerted at an angle of 30 degrees above the horizontal. Then there's a coefficient of kinetic friction, right, between the box and the surface. So remember, it looks like the motion of the box is going this way because that's what the tension is pulling. And friction always goes in the opposite direction of the motion. Now, we also know that the normal force is going up, and that the weight, remember this is the weight, but it'll have a negative value because the acceleration due to gravity is going in the negative direction, right? Yes.
Why do you zoom all the way in? Is it just show the answer?
I didn't zoom all the way in, and I copied and pasted this.
Oh, okay.
Okay. So anyways, so now what they really want to know is which of the following is the correct mathematical equation derived from applying Newton's second law in the box. So that's a really weird way to ask what's the acceleration, right? Because Newton's law is that the acceleration is inversely proportional to the mass of the object. So when we talk about Newton's second law, we're talking about this. Force is equal to the mass, but they used a capital M. Capital M times the acceleration. So if I divide both sides by the capital M, I get that, and I'm going to write this down here. That's Newton's second law. Yeah. Oh, I see what you mean by zoom in.
I know you showed that answer. That's why you wanted to zoom in.
No. I wasn't. Because last hour. Okay, I'm sorry about that, guys. When you said zoomed in, I was like, I'm not zoomed in. I copied and pasted it. All right, okay. So can you guys see that now?
Yes.
All right, cool. So I'll give you guys a second. I didn't realize that was zoomed in so tight on the screen. So when I do the math on that, this cancels with this, and so what I end up with is on the bottom I get the acceleration is equal to the force divided by the mass of the object. So this has a mass. Now, I don't know what the numbers are, okay? But when I talk about the force, I'm talking about the force that causes it to move. So we're really talking about the force in the x direction. So that's a little x there. So that means that the acceleration is equal to the net force, or the sum of the forces in the x direction divided by the total mass. Okay. Well, I know a couple of things. When I say x direction, I have this force here, and then the other thing I need to think about is I'm going to need to think about the x component of the tension. That's it. I don't care about the y components. I only care about the x. Okay? All right. So I guess I'm going to have the tension of the rope, but just the x part minus the friction. all over the mass. You guys with me so far? Does that make sense?
Yes.
Okay. So how do I find the friction force? Well, if you don't remember how to do the friction force, remember that the friction force, lowercase, I always think of fun because it kind of looks like fun, but it's the coefficient of friction times the normal force. Well, the normal force is just the positive value of m times g, right? But it's going in the opposite direction. Now, how do I find the tension force in the x direction? Well, isn't that just T times cosine of the angle theta? Yeah. So then I'm going to have to wait, let me think this through. I wonder if I'm forgetting something. I don't think so. Let me think for just a second. So I've got T cosine of theta minus the friction force, which is going to be mu times the normal force. All over m. Oh, wait a second. I am forgetting something. Well, friction normally is just the normal force, but there's another force that's going up, isn't there? Yeah, T sub y. Right? T sub y. Well, not for the x direction, but remember that has an impact on the friction, right? Okay, so now here's a tricky thing. So on the next line, we're almost there, guys. We're not that far. We're almost done. We got like one more line. So when we go to think about the normal force, so basically this part is the same. Oh, I think I ran out of room here. Yeah. So we've got T cosine of theta. Let me see if I can slide over a little bit. No. I'm just going to move this down here. And zoom back in so we can see it better. So I've got T cosine of theta minus mu times, technically the normal force goes up and weight comes down. So really what I'm thinking about is what opposes what? Well, the normal force usually is mg. So this would be times mg, but I have to subtract the y component of the tension. Because mg, we say the normal force, but when you think about it, the normal force, if we weren't pulling at an angle, the normal force would be equal to the weight but going down. But now, instead of the normal force, the magnitude of the normal force would usually go down. And so think about friction. The more force I have pushing down on an object, the more friction I'll have. Okay? That would normally be mg. But I have this rope that's pulling up just a little bit. And so gravity's pulling down, but the rope's pulling up just a little bit. I have to subtract that. I have to oppose that because of what we're doing with friction. Does that make sense? Okay. All right, cool. So then in the next line, to finish that. So this is the acceleration. We're almost done. So then the acceleration is, how do I find t sub y? Does anybody want to jump in on that action? Minus, it's the same equation as x, except t sub y, whoops, wrong color. Yeah, you just use sine. So t sub y, the tension in the y direction, is just equal to the tension times sine of theta. Right? So way down here, I'm going to say mu times mg minus the tension sine of theta. All over the mass. And then that's it. Any questions to that? Okay. Now the only part that's confusing about is the normal force usually goes up, but when we apply it, we're really thinking about it theoretically, like from a conceptual perspective. Friction is the contact between two surfaces. So we always use the normal force because that is perpendicular to the surface of the motion. But because we pulled at an angle, we had to have the opposite. So anyways, any questions on that? Okay, so that's the final answer for that one.